Hello students, today's agenda is to check homework. You will be working on the explicit formula, specifically related to geometric sequences, and you will be able to do 7.4. So today's students will be able to find the explicit formula for geometric sequences. Forget about that if, sorry. And so I want you to think about this. Okay. Suppose that on the first month you have 2 rabbits. On the second month you have 6 rabbits. Excuse me. On the third month you have 18 rabbits. On the fourth month you have 54 rabbits, and so on. How many rabbits will you have on the 15th month? And if you recall from the recursive formula, to be able to find out how many rabbits you have on that day, we have to go back and then see that what's happening is that you're multiplying by 3. And so you would have to multiply by 3, by 3, by 3, by 3 until you get to the 15th month. Okay, so let's start with the sequence. So if we see this as the sequence, we would start with 2, then we would have 6, then 18, then 54, etc., etc. And if you think about it, if you need to write it, maybe you want to pause it. But if you think about it, so what does each of these mean? If we observe, so if we think of months, on the first month I have 2. On the second month I have 6, and this 6 comes from me multiplying 2, which is the initial point. And I'm multiplying by 3, multiply by 3, multiply by 3, which makes it a geometric sequence, right? So it comes from multiplying 2 times 3. The third month, I have 18, which comes from multiplying the 2 times 3 and times 3 once more. And then on the fourth month, I have 54, which comes from multiplying 2 times 3 times 3 times 3 again. And if we write this in, we look that we have several 3s, then it comes from multiplying 2 times 3, and we can put this between parentheses, to the first power. This one comes from multiplying 2 times 3. How many times do I have the 3? Twice, so to the second power, or squared. And then this is 2 times 3 to the third power. So how does it relate to the number, that exponent? How does it relate to the number of the month? If I'm looking at month 3, my power is 2. If I'm looking at month 4, the fourth month, my power is 3. What does that mean? That means that I'm looking at the number of months minus 1, right? Because 3 minus 1 is 2, 2 minus 1 is 1, 4 minus 1 is 3. So I'm subtracting 1 from this to put in the power. And if you notice, this is my initial point, and this is my pattern, which is my pattern. Which is multiplying by 3. I'm going to say that this also has a different name, which is called common ratio. Whoops, common ratio. Okay? So I just call it the pattern because that's the rule that we're applying, but it's also called common ratio. So if we're looking for any non-specified day, Okay, we just put n, the n month. So I'm going to have f of n is equals to my initial point, which is 2, my common ratio or pattern, which is multiplying by 3, and what did we say? How does this relate? Always the number of the month, which is n, and take 1 away, right? With 1 less, 1 less, 1 less. So that's why it's n minus 1. So this will be my explicit formula for this specific scenario. Explicit formula. And again, now with the explicit formula, you don't have to really go back to doing number 5, then 6, then 7, 8, 9, 10, 11, 12, 13, 14, until you go to the 15 month. You don't need to do that because the explicit formula will allow you, excuse me, allow you to find any date you want without having to do the previous one. Okay, so now let's find for that one 15th month. How many rabbits will I have after 15 months? So I'm going to put f of n, but instead of n is 15, my initial point, my common ratio or pattern, and raised to the power of n is 15 minus 1. Remember, it's always 1 month less in the exponent. And so this is going to be 2 to the third power times 3 to the 14th power. And now I'm going to ask that you bring out your calculator, hopefully at least a TI 30 or a scientific calculator will do. And you can directly find, actually I'm going to do it directly so that you can see, but I will also show you step by step. According to PEMDAS, we have here multiplication and exponent, but according to PEMDAS, we do the exponent first. So in the next step is going to be 2 multiplied by, and whatever we get, I shouldn't have put that in there. Whatever we get by raising 3 to the 14th power. Okay. And so in your calculator, you're going to press the key 3. You're going to, if you see this key right here, it says y to the x. That's the power button. You press it, and then you put the exponent, which is 14, and then press equal. Okay, so that's why I said I shouldn't have put that in here, because it's going to be a bigger number than the space I left. So it's going to be 4,782,969. Then I multiply that by 2, so times 2 equals, and then I get that I'm going to have, after 15 months only, I'm going to have 9,565,938 rabbits. Okay, so my input is 15 months, my output is 9,565,938 rabbits. Okay? So, again, how do you write an explicit formula? For a geometric sequence, geometric is when you're multiplying. In here, you're multiplying. You always have f of n. You always have your initial point. You have, since it's multiplication, you multiply times 3 in here in this case. And then n minus 1 is going to be exponent. Why? Because we're multiplying 3 times 3. So we're multiplying 3 times itself 2 times. We're multiplying 3 times itself 3 times. That's why it should be, the n minus 1, it should be exponent. Okay? Yesterday we learned about adding and subtracting, which is arithmetic sequences, and then this is not in exponent, is next to the pattern, which is a factor, not an exponent. Okay, so I think it's going to be easier to understand once you see another example. And so let's see. Let's try this one now. Find the explicit formula for, again, the other process was a little longer just because I wanted you to understand it, but in here we're just going to go directly to what the things that we need. Find the explicit formula for 4, 8, 16, 32, 64, 128, 256, 512. What we need is the initial point. We need to see what's happening from here to here. And some people say, oh, we're adding 4. But then they notice, oh, we're not adding 4 in here. We're not adding 4 in here. So what we're doing is multiplying by 2. Multiplying by 2. Multiplying by 2. Oh, so we're doubling. Okay, so my initial point is going to be 4. What we're multiplying by, which is called the common ratio, is times 2, and you can put parentheses or a dot, it doesn't matter. And so my function would be f of n is equal to my initial point. Remember, we're multiplying, and when we're multiplying, n minus 1 is not going to be here as a factor. It's going to be up here as an exponent. Okay? So that's how my explicit function for this sequence will look like. Initial point, the common ratio or pattern, and n minus 1 is going to be an exponent. Just because we're multiplying, it's going to be as an exponent. Okay? That's all you have to do. The other one was just to understand it. Okay, let's try another one. So initial point is, you will see that it's going to get easier and easier. 2,000. What's happening in here? Somebody says, subtract 1,000, subtract 1, oh, never mind. We're multiplying by 1/2. Remember that when you see that it's going by 1/2, 1/2, 1/2, it means that you're multiplying by 1/2. Some people see it as dividing by 2. Dividing by 2 is the same thing as multiplying by 1/2. Multiply by half. Okay, so the common ratio or pattern is to multiply by 1/2. So my function f of n will be equals to my initial point. My initial point multiplied by the pattern, because it's a geometry, we're multiplying. And every time that is multiplication, we put n minus 1 as an exponent. Okay? And with this, we can figure out how much money I will have after 10 days, after 100 days, after, okay? So it doesn't matter. With the explicit formula, you can go directly without having to find every single one in the sequence. With the recursive formula, you have to find each one, because to figure out this one, you depend on the previous one. To find this one, you depended on the previous one. Okay, let's try a couple more. And I'm gonna really fast do the initial point for all of them. It's 3 different ones. In this one, what I'm doing is multiplying by 3. Whoops. The pattern is to multiply by 3, multiply by 3, multiply by 3, and so on, okay? In here, it looks like I'm multiplying by 2, multiplying by 2, multiplying by 2, etc., etc. You're doubling. And for the last one, it looks like you get half of the previous one, so you're multiplying by 1/2, multiplying by 1/2. So I have the two important things for every single function. And so I can say that it's f of n equals initial point times 3, because that's the pattern. And since it's multiplication, n minus 1 up there. Okay? F of n equals initial point, and the pattern is to multiply by 2, and because it's multiplication, then n minus 1 is a power, an exponent. For the last one is f of n equals the initial point, and I'm multiplying by 1/2, and remember n minus 1 should be a power, an exponent. Okay? Okay, so that's how you come up with the explicit formula when you're given a sequence. And again, all of these are geometric sequence because you're multiplying. Okay, let's try now to find the first 5 terms if you're given the explicit formula. And what you want to do, I'm going to leave space here to write the sequence or the first 5 terms. What you want to do is you're going to find the first term. So that will be f of 1. Okay? F of 1 equals 4 times 2 to the n is 1 minus 1, which is equals to 4 times 2 to the 1 minus 1 is 0. 4 times, now I want you to know, and you probably learned this before, that anything to the power of 0 will always be 1. Okay, if we have 5 to the 0 equals 1, 2 to the 0 equals 1, 1 million to the power of 0 equals 1. Okay, so in here this becomes 1. And 4 times 1 is 4. So that's my first term. To find the second term, I'm going to put f of 2 equals the initial point, the pattern, and then my n is 2 minus 1. So all I'm doing is plugging in my n with that second number. And so it's 4 times 2 to the 2 minus 1 is 1. Anything to the power of 1 is the same number. So it's going to be 4 times 2, which is equals to 8. So that's my second term. Now for the third one, I'm going to put f of 3. And so that's equals to 4 times 2 to the 3 minus 1. 4 times 2, 3 minus 1, 2, which is 4 times 2 to the second power is 4, and 4 times 4 is 16. So that's my third term here. I can see that this is my initial point, and it looks like I'm multiplying by 2 for my pattern. So that pattern can help me to figure out the rest of the terms without having to do this 5 times. So times 2 will be 32, times 2 it will be 64. And those are my first 5 terms. Okay, so we have one more in here. And so you're going to have to do the same thing. I'm going to leave some space in here to write the first 5 terms. And so f of n becomes f of 1 to find the first term. And so it's going to be 4 times 3 to the... Now you notice that it doesn't have n minus 1. This has been simplified, this function. So all you have to do is just worry about what we have and plug in the one in here and the one in here. Okay, and so this is 4 times 3 to the 1 is 3, which is equals to 12. F of 2 is equals to 4 times 3 to the second power. Again, in here, the formula doesn't ask me to subtract 1, so I'm not going to subtract 1, okay? Just because they're giving it to me, simplified already. So 4 times 3 to the second power is 9, which is equals to 4 times 9, 36. I do one more. Sorry, I just moved the phone. F of 3 is equals to 4 times 3 to the third power. And that's 4 times 3 times 3 times 3 is 27. And that gives me, let me see, I'll use this one right here. 4 times 27 equals 108. 108. So what is going on? Oh, I'm multiplying by 3. So I can just multiply this by 3. And the next one is 324. And times 3. And the next one is 972. So I recommend that you do the first 3 terms using or replacing by 1, then by 2, and then by 3. And then after that, you can check what the pattern is and just apply it to find the other ones, the other terms in the sequence. So now you're ready to do 7.4, and I hope you have fun.